saw the schedule. I am not Fawaz Ghali. He's one of my colleagues. He unfortunately wasn't able to travel to this conference, so I am taking his place. We both work at Hazelcast, though. I'm a senior solutions architect with Hazelcast, so I help on the technical side of selling to try to help customers understand how we can integrate into their environments. And the topic today was 5 challenges with real-time stream processing and how Hazelcast can help you solve those. So first thing, just kind of want to talk about stream processing versus real-time data stores and kind of tell you a little bit about what Hazelcast does before we get into how we help solve these things. So on the right-hand side, you have your fast data stores, right? Which could be NoSQL databases like Mongo, like Cassandra, like Couchbase. Could also be in-memory data stores like Redis or SingleStore. And on the left, we have your stream processing engine. So things like Kafka Streams or Flink or Kinesis Data Streams. And where Hazelcast sits right in the middle, because we do both. We have the in-memory data store side that we can store your data at rest, and we have the stream processing side, so we can process your data in motion and combine those together so that there is no out-of-memory hops, there's no network hops that are needed in order to access extra data when you're doing that stream processing. This next slide kind of really, I think, there's a lot here, but I'm going to walk through it. It wraps up what Hazelcast does. So there's really 2 views. There's the north-south, which is our in-memory data grid. And so the in-memory data grid is a clustered, resilient cache, essentially, that will sit on top of your data stores, your data at rest, and allow for all of your applications where we have clients written in basically any language you would want to use, and to be able to connect to that, and you can connect to it through these APIs or through just a SQL interface to query, update, delete, whatever, all of your standard CRUD operations, as well as SQL queries into your the data that you might have down here. But to do this in a very fast, high throughput, very low latency way. The west to east side is our stream processing engine. And this is where you can take data from whole variety of sources that you have here. So basically take data in flight from anywhere and run that through the stream processing engine, which again is in that Hazelcast cluster. So it's going to be distributed, so it's distributing that compute across the cluster to allow you to do things like transforming or combining data between streams, combining data between your stream and your in-memory data grid, to run machine learning models, to do essentially whatever types of streaming jobs you need to do, whatever types of work you need to do on that data, and then spit that out somewhere so that something else can make use of whatever it is that you were doing. Kind of getting a little bit more into the deployment architecture. So what I was showing here, essentially this would be one node in Hazelcast, that comes with the streaming side and the in-memory data grid all in one. And in our clustered environment, all of these nodes are peers. They're all able to talk to each other, to communicate with each other. On the data side, each of these will be holding pieces of the data. It's all striped across there. And there's backups to that as well, so that there's resiliency. So in case any node goes down, that's fine. You have backups already. You don't lose anything. Compare that to more of a traditional type of distributed architecture where there's going to be a master node that ultimately delegates to worker nodes and is able to, and then even underneath those, a lot of times there'll be HDFS nodes or other things. And the real problem comes when something happens to the master node. Well, then you oftentimes end up losing data, or you end up losing your state for where you were with processing. And it's a lot more complex to recover from than if you lose a worker node. The final kind of intro to Hazelcast is just sort of comparing us to other real-time data platforms and really, I guess I would say, data lakes in general. So again, they're able to take data from relational sources or from streaming sources and then run that through some kind of preparation, right? So you do your aggregations, do your data augmentations, do your transformations, do whatever you're doing. But each of these steps is A, a discrete step, and B, it's gonna be rewriting that data, rewriting that data, rewriting that data. So you take your 10 terabytes of data and turn it into 50 terabytes of data because it has to keep rewriting it, rewriting it, rewriting it as it's making all of these changes. Then ultimately pushing that to a real-time data store like your Redis, like your Couchbase, like your Mongo, to make it available for analytics, for applications, for whatever to talk to. Hazelcast, though, says, you know what, you don't need to do all of that. We can do all of that at once in memory, so you don't have to go through all of these steps and storing all of that extra data and then making it available. And then, right, we do all of that at once in memory, and we can automatically spit out actions that you might want to take. So there is no human intervention there. You can automatically say, hey, this person, right, there's this credit card transaction looks fraudulent. Or if we're monitoring medical devices, hey, you need to take a look at the patient in room 213 because, right, their blood pressure is getting too high. Whatever the thing is, spit out those automated actions. Oops, sorry. But also making it available for your applications to call. And in case you have that legacy application that will only work with MongoDB, for example, and so you have to make sure that that data is ultimately in Mongo for that to work, okay, that's fine. We can push that data out into Mongo as well, or into wherever else it needs to go if there's other data stores, data applications that need to have it. To get a little bit into the streaming side, so again, you can see this green box would be a Hazelcast cluster. And so this would be a group of nodes that are all running together, and each of these cyan boxes would represent individual nodes in that cluster. And so we can be listening to your event stream input, whether that's Kinesis data streams, Kafka, whatever that is, that's sending in events. And each of these are listeners to that. Each of these can take up that data and begin processing it, doing whatever you need to do, whether that's queries or if you have some other type of logic, and ultimately pushing that out somewhere. And one of the newer use cases, as this is showing here, is MLOps. So being able to run machine learning models in this distributed environment. And what we've seen there is we have some customers who previously were able to run one model within their SLA, but then when they switched to Hazelcast and using our distributed environment, they're now running 8 models in the same time that they previously were running that one model and combining all of those results. And through that, they were able to save $100 million a year in fraud losses by just being able to run all of these extra models. But now, to get into what the presentation was actually about, what are the 5 challenges of stream processing? So the first one is scalability, right? What are you gonna do when you start having more requests coming in than your stream processing engine can handle? And do you have bottlenecks in there that maybe, right, that there is that one master node and everything has to go through the master before it can get to the worker? So things like that. Well, Hazelcast is all containerized. So if you're using Kubernetes or OpenShift and you have CPU monitoring, you can see, oh man, we have exceeded how many, we're getting pegged here. Just start up new pods. And then they can immediately join the cluster. They can immediately pick up work and start processing. Additionally, if you want to just spin up new nodes on bare metal or through VMs, okay, that's great. You can start those nodes up automatically, and they'll join the cluster as well. And again, I'll automatically start taking in work and processing that. And it's been proven out with linear scalability. And I'm going to get more into this in a little bit, but this is actually from a third-party benchmark that was done, where you can see that as they added more nodes, it just linearly scaled and was able to handle more work. So if you need it to go faster, add more nodes, and it'll linearly scale for you. So the second challenge is performance, and especially, right, does your latency start to suffer as you get more and more throughput? Hazelcast helps solve this because all of that compute that we're doing it's distributed across the cluster. We have intelligent thread management that knows, hey, this new job came in. I'm going to break this job into steps. And so it's all of your jobs are written in Java code, by the way, using the Java Stream API. But we extend that for Hazelcast then to be able to break those up into steps. Then it'll know, okay, well, this step is done. Oh, hey, this node over here has free CPU. Let me move that over there so that can do the next step. Oh, and then now this node has free CPUs. Let me move over there to the next step. And so it'll intelligently find where is there compute in your cluster and use whatever CPUs it can. And so it'll leverage any available threads anywhere in the cluster to automatically pick up and do the processing. So we don't have those issues with performance and with starting to bog down because it'll automatically find wherever there is available CPUs. The next big challenge is failover. What do you do if a node fails in your cluster? What do you do if the master node especially fails? And the big question, right, is state maintained. If a node does fail, do you have to restart this entire job or do you pick up where you left off? Well, with Hazelcast, there is no master node. Everything is peers. So any node goes down, that's fine. It's all, as I mentioned on the resiliency, it's all backed up already anyways. And so there isn't gonna be an issue in terms of do you lose state? No, because we have that in-memory data grid, so everywhere along the way, whenever the streaming does anything, it automatically is saving the state into the in-memory data grid so that if something happens to a node, well, the state is saved. It can pick up that state from the data grid and immediately start processing that on another node. So there is no worry about if you fail over, well, that's fine. There's other nodes in the cluster that can take over immediately where that left off. Then reliability. And so reliability really has a few things here. One, in general, is your performance reliable? Or will you see that maybe sometimes, well, on average, it takes 30 milliseconds, that 1 in every 10 requests takes 3 seconds, and you don't know why. Or is it deterministic, right? Are you gonna get the same answer every time with the same input? Also, is there any guarantees that you will get a response? And what are those guarantees? Is it gonna give you at least one response, or could it send it back multiple times? And so understanding all of those. So going to that last one first, so it's all configurable at the job level in Hazelcast for how you want to do that. Do you want to get at least one response? Do you want to get at most one response? Or do you want to get exactly one response? And you can configure one or more of those at the job level using the Chandy Lamport distributed snapshotting algorithm. And so you can, if you're interested in that, they did a big paper on this, and we borrowed their exact algorithm that they used to put into this, which is exactly what I was describing in the previous slide about saving state along the way, then picking up if anything happens from that saved state. And again, there's performance without hiccups because of the fact that it is distributed compute. It'll automatically see if something isn't responding within time, and we'll just start picking up and running on another thread. And it is completely deterministic. If you send in the same input, you will get the same output, as long as none of the underlying data that you might be using in the data grid changes. Finally, data recovery. So again, what happens if you're saving your state in an offline storage and that offline storage goes down? What happens if you're reading in data from someplace and that data that you're reading it in from goes down? Your network connection to it goes down. Well, in Hazelcast, that isn't an issue because we have the in-memory data grid in memory with the stream processing. So there is no offline. It's all in memory already. And if you do need to call like a REST API, or you have to do something to access external data for some reason during a processing, that's fine. It's all, you can customize how you would want to handle that if that REST API or that connection that you need to make isn't available. And so, right, I've been talking a lot about performance, and you can see my shirt, right? Speed matters. And so that is one of the things that we really pride ourselves on. And this is a third-party a third-party benchmark that was done by Nextmark to test that, to test how much can they push through, to test our scalability. And they were able to do 1 billion transactions per second with 99% of those under 30 milliseconds of latency through our stream processing engine. They did this on AWS just using C5 nodes, so not massive nodes, right? Kind of your standard size worker node. And they had just 45 of them, and they were able to do 1 billion transactions per second. And it scaled completely linear. And the latency stayed the same as it was scaling. So obviously a lot of companies don't need 1 billion transactions per second, but that's the whole idea of the linear scalability is you say, okay, well, we just need 100 million transactions per second, then okay, well then you could do that with 5 nodes or 6 nodes or whatever it ends up being. And so, right, that's the advantage of, and maybe there's also some companies that need 10 billion transactions per second. Well, okay, we're working on that benchmark now to show that, okay, well, with 400 nodes, you can get 10 billion transactions per second then. And so it will really scale to whatever your needs are. In terms of latency, so I don't know if you guys can read this. I know the print's kind of small. You'll see that there's 3 bars for each of these, and this is all based on throughput. And one of those, the bar in blue, is labeled Jet. So our streaming product used to be called Jet. In the most recent, in the release that came out last summer, we actually combined the in-memory data grid and the streaming that was called Jet together into one product. But this was done, this benchmark, go back there, was done when it was a separate product. That separate product was called Jet. And so this is just showing that as you're throwing more and more throughput into Hazelcast versus Spark versus Flink and seeing how the latency works. And you can see that with Hazelcast, our latency is staying the same throughout. It doesn't matter how much throughput you're throwing in. But with Spark and Flink, they're both starting to get a little bit slower, a little bit slower, a little bit slower, the more work you're throwing at it. So in general, best practices that Hazelcast kind of has laid out and has built our entire platform around is the idea that you can ingest your data in any format. You don't need to do standardizing, cleansing, transformations, whatever. We'll take whatever your data looks like, whether it's XML, JSON, relational data, flat file data, whatever, throw it to us. We'll figure out how to handle it. You can build all of that into Hazelcast. You can use SQL to analyze that data, even if it's not SQL data, even if it's a flat file, even if it's JSON or POJOs that you're looking at. That's great. We've built our SQL engine to still let you use SQL for querying that data. You can query data across streams. So if you have multiple streams that you know are coming in and you want to combine those or union those in a single SQL query, great, we let you do that. It will allow you to do real-time aggregations and windowing. So when your data is streaming in and you want to see, count, I don't know, how many transactions came in within the last 10 minutes that met this criteria. We can give you that all the time in real time. If you want to count how many, I don't know, whatever aggregations you want to do, yep, they're built in. You can do those. The whole idea of this is to get rid of disk I/O. You're not writing to disk anymore because we're saving it all in memory. And so there isn't the disk I/O that you're having to worry about, so that you can cache at scale. You can run your streaming at scale. You can use that real-time data for whatever purpose you have, right? So it's always going to be available, and it'll be available the instant you need it. And the whole idea is to focus on simplifying your code. So we built all of our clients. Our clients can be used in whatever language you want to use. We support all of those clients, but we also support simple SQL syntax everywhere as well. So you can decide what language you want to use to write your clients in. You can decide how you want to be connecting with Hazelcast. It's set up for our customers that can't take any downtime, right? We have customers that are banks or that monitor medical devices or that, right, do all sorts of different things that downtime is not an option. And even if you want to do upgrades later, we have rolling upgrades built into the product so that then you can, right, just update one node at a time and get the entire cluster up to the latest level without anything in the node ever having to go down. And the last best practice, avoid the enemies. And so what are the enemies? The enemies are network hops. If you have to move or call data something else, call another microservice somewhere else, call whatever, keep everything within the cluster. Again, I/O. Don't use the disk if you don't have to. Do everything in memory, do everything as fast as possible. Avoid I/O. Avoid processor context switching, right? Allow each thread to do whatever it can, and then within that job step, and then if you need to move to another thread, that's great, but don't make one thread start and stop and start and stop and start and stop. Just keep doing whatever you can on that one thread. Avoid this unnecessary steps in your architecture, right? That's where we keep everything within the cluster. Everything can be done within the cluster. You don't have to go out to other nodes. You don't have to call out to external data. You don't have to, everything is self-contained. And you can do your data enrichment, whatever data manipulations you want to do without having to do external data retrieval. You already put that data in your in-memory data grid, then your stream processing already has it. You don't have to, with some technologies like Confluent, for example, you want to combine data at rest and data in motion? Well, you actually then have to pre-query all that data at rest and pass it in to your KSQL in order to combine those. You don't have to do that here. We already have all of that saved in memory. And so you can automatically utilize both of those together. So if you want to learn more, Hazelcast has an open source version that anyone can download and try it out. There's also a free 30-day enterprise license, so if you want to try out the enterprise features. And we've also launched what we call Veridian. So this is our managed service that's available that you can try out. I think right now it only works on AWS, but it's going to be scaled out to work on AWS, Azure, or GCP, and connect to your own VPCs. So if you have data already out there, you can do VPC peering and be able to connect to data that you might already have out there. Additionally, we have a Hazelcast developer community. So there's a Slack that any Hazelcast developers can get on and ask questions, and there's full-time people that they answer questions from the developer community. We held local events in various places, like typically once a month or so. There'll be various remote events that are going on that could be local to wherever area. If you guys all come from the Chicago area, I think we had one earlier this year here, but there's always different local events. There's also Twitch live streams, YouTube live streams that we do to show different use cases, different technologies, different things that you could do with Hazelcast. And we have a Hazelcast Heroes program where this could, become somebody in the developer community who really knows Hazelcast, champions Hazelcast, and can help us by speaking at events like this. So if you're interested in the developer community, we have an email address here. You can email them, and you can find out more. And now, I guess I'll just open this up for questions that you guys might have. Yeah?
One slide you mentioned that there is no master node actually, right?
Right.
Every node is like a worker node. So for example, if one node is down and then it's in the middle of the processing, how another node will know that I need to pick that one master?
Yeah, so that's a great question. So all of the nodes that will have basically will know that all of the other nodes exist. And so all of the nodes are kind of listening to the other nodes, and there's a ping that happens every 10 milliseconds by default configurable, but most people don't change that. That's listening to all the other nodes. And to find out if something happens, then once the first one notices, then it will either kick off, so on the data grid side, it kicks off what we call a rebalance, which then essentially figures out, okay, who had the backups for whatever that data was on that node, it's to bring those backups to be real. And so as the master, if you will, for the data, But on the streaming side, it will also realize, hey, that node went down. It was doing these 3 jobs. So all of the state has been kept in the in-memory data grid side. So then it will, again, there's an intelligence in the stream processing side to figure out which nodes have available compute, and it'll pick up exactly where that job left off. That was saved by the state.
In that way, like, there is no controller per se?
So the controller is distributed essentially across the cluster. And so each node is a controller. Yeah. Yeah.
So on the similar lines, right? So are there any tools, controls, or any kind of reconciliation that needs to happen, or from a user perspective, should I be concerned about the data that is living in these clusters? Is it always current? Are there ways or way to find out if the data is not in sync? Any controls?
Yeah, so we have an API, or sorry, not a GUI called the Management Center. And the Management Center will let you look at all of your nodes, and you can even, in all of your clusters, because you might have multiple clusters. You can connect this to any of your clusters, view all of the nodes, see all of the data, and it can also highlight any inconsistencies with the data to allow it. And this is, again, kind of, so it's one of the answers. If you talk to Hazelcast more, you'll hear, oh, it's configurable, it's configurable. So if you want to automatically handle inconsistencies, that's built in. There's different models and ways you can handle inconsistencies in data, or you can percolate it up to say, no, I want to manually solve this, in which case you look at the Management Center, and the Management Center will tell you, hey, there's something going on, there's an inconsistency between node 7 and node 8. How do you want to resolve this? Yeah.
So, like, you mentioned one of the best practices, like avoid the network hops. So it's not like recommended that you do a stretch cluster here.
It's not recommended to what? I'm sorry. Yes, yeah, you do. So we would, yes, highly recommend, and it's in our documents. Don't have stretch clusters. Run all of them within a single data center, within a single LAN. And we do have a feature that's called WAN replication, which would let you have multiple data centers, if you want to run on multiple clouds, if you want to run your cluster in the cloud and on-prem, and it will automatically keep those clusters in sync. Again, it's configurable at the cluster level to say exactly how you want to do that, but yeah, it'll be able to keep them in sync, that you can do active-passive or even active-active if you want, between your clusters running in different environments. But yeah, if you are running across network connections, it's highly, highly recommended that you use that WAN replication feature, because otherwise the problem is that if you have a stretch cluster, I was mentioning that every node is constantly pinging other nodes, and it's 10 milliseconds by default. And so if that ping time is longer than 10 milliseconds, which will happen a lot on the stretch cluster, it'll say, oh, that node's down, let's rebalance. Oh, the node's back, let's rebalance. Oh, the node's down, let's rebalance. Oh, the node's back, and so it's spending all of the CPU rebalancing rather than being able to do what it normally would be doing and allow the CPU to be used for streaming. Yeah. No, feel free, this is.
So in that one of the diagrams you had that you have a query which you can feed, right? So that's like a static one. I have like I put the cluster as a shared service, and I feed the query and run and connect to that. So I'm running the nodes like 45 minutes of usage.
Right. Okay.
I have basically I'm just treating that cluster or nodes as like a shared cluster. I want to feed the query in the runtime and different queries as an connect.
Yes, yeah, there's definitely, if that's what you want, yes. So basically the data streaming in can be whatever you want. Yeah, it can be queries. It could just be a piece of data that you want it to do something with. It could be, I mean, it's really open and flexible in terms of what do you want this incoming thing to be and to do. The querying, though, typically is going to be done through clients and querying the data grid itself. But as I mentioned, you also could run queries between stream jobs, right? So maybe you have, I don't know, 5 different Kafka topics, and you need to be able to do joins between them, and you can, send in queries then you can have real-time aggregations or monitoring or windowing of all 5 of those different streams all at the same time. Yeah.
Yes. As far as scaling goes, I assume that's kind of the job of the cloud environment to scale up nodes.
Yeah, I mean,
You could have like underutilized nodes ready and waiting for tasks.
yeah, if you want, if you're using it in the cloud, you can definitely have that. Same with Kubernetes, right, or OpenShift, that you can set it up to automatically scale up, scale down based on CPU or memory utilizations, and it's really pretty configurable again in the scalability as well for when you want to scale up, when you want to scale down. So you can, and you can use, right, if you want to use like the GK, man, I forget what it's called and all the different things, but right, if you want to use AWS's Kubernetes environment or Google's Kubernetes or Microsoft, you can build it in there. You can roll your own, and right, we have an operator that's available. We also can use Helm charts, so it's really however you want to configure to use it within your container management, then it's open and available for you. I guess I should have said here too when I was saying about, this one. So also on all of the marketplaces for the different cloud providers, we're available there as well, but it is paid. So I don't think that there's free trials on those. There is the free trial though on our Viridian, which if you go to this website, you can find out all about it. It'll allow you to set up, it's pretty small, the cluster you can set up, but still it's a free for life as long as you stay within the bounds of that free trial. All right, well, if there aren't any other questions, thank you for taking the time listening today. If you do have any other questions that maybe you want to ask me or find out more about us, we do have a booth downstairs. Happy to see all of you guys here, see this attendance here, and happy to talk more if anyone has any other questions. All right, thank you, everyone.